Hello YouTube, today I'll be making a quick tutorial on a topic that I've always wanted to cover, and it's called binary index tree, or Fenwick tree. So this is how it's spelled, binary index tree or Fenwick tree. And the main idea of these tree data structures is to provide a mechanism that allows you to do range searches and range updates very efficiently. So let's cover one of the original problems in computer science. Given an array of elements, of size n, determine the sum from indices I, j, let's say. So we have two solutions that we can come up with right off the bat. So one solution would be having the implementation approach where we actually perform the summation throughout everything. So this would be O(n) time, so this would be per query. We would have, let's change up the colors a little bit, make it special. So we have O1, O(n), O1 and O1 for the query, update, and space. This is sort of like our naive approach. Okay, so this is the very first approach. So we literally just go through the entire array one by one. So if we have an array that's like 0, 2, 3, 5, 7, 9, we would manually traverse through the array, adding up all the elements from here to, let's say, here. Okay, so this is like the naive approach. We can call this the summation approach. Alright, well, one observation is that the sum of different ranges, we can pre-compute it using the prefix sum arrays approach. So the prefix sum arrays approach deals with a concept from actually the fundamental theorem of calculus. So we would have, let's call this like that. The idea is if you use the fundamental theorem of calculus and you compute the definite integral over an area of the graph, you can find out the area of that graph using just simply taking the antiderivative of the function at the 2 points. So if we have a graph that, say, that looks like this, and then we have some values over here, right? And you want to compute the summation of elements within this range. Let's say this is like 100, 200, 300, 400. Well, we would be taking the definite integral, which is f of 300 minus f of 100, and then we had plus c minus c, which cancel out. So this is the main idea, is that we can pre-compute this prefix sum array over the entire array. But as we will quickly notice, we will see that, hold on, my pen stopped working. We will soon notice that it'll actually take more time. Hold on, my Apple Pencil seems like stopped working. It will take more time to actually compute it, because our query time will be O1 because we already have the antiderivative. But in order to compute that antiderivative, we will need to have an O(n) update time. And that, unfortunately, is a little bit slow for our purposes. So let's see if this pencil works now. Okay. So we get O1 query time, but we get O(n) update, and then we also need an O(n) data structure in order to facilitate all this. So our query, update, and space. So why is it O1 query? Because in O1 time we can actually pre-compute this component over here. But in order to calculate the antiderivative of it, the antiderivative of the function, we'd actually need to manually create a summation of everything from the beginning and then be able to use this antiderivative function. So now that we have these two approaches, we're going to be introducing the more improved approach, which is the binary index tree. So the binary index tree will allow for binary index tree approach will allow for log n query, log n update, on space. So overall, not so bad. Not amazing, but this is an alternative to the segment tree approach. So the segment tree approach is more complicated than this approach. This is, as you will see, a very simple implementation, but it's very powerful, and then it can be used very quickly in things like algorithm contests or if you have an interview. So what is the actual guiding principle behind the binary index tree? We see that the naive approach is fairly simple. The prefix sum approach builds on top of the fundamental theorem of calculus. So what is the purpose of the binary index tree approach? Well, the intuition behind this approach is that if we have any number x, we can sum it up with different powers. This is always true. We can always find some set x1 to xk such that the following is true. And this guiding principle allows us to sort of construct a tree and manipulate bits in order to have this ability to express it as a summation of powers. So what does this all mean? Well, we're going to get straight into an example here. If we have a number, let's say, and hold on, I got a little sheet here. We have an original node up here, and then we have some children nodes to it. And I'm going to say that this node represents 0. This node represents 4. This node represents 2. And 4 has 2 children that are 5 and 6, while 2 has a child that's 3. Okay, where did I get these from? Let's take these numbers in binary now. So 0 is 0 in binary. 2 is 1 0 1 1. 1 0 0. 1 0 1 1 1 0. One of the key things you need to notice here is that when you go from a child to a parent, you're always removing one of the bits from it. So there's actually going to be one more here. One more node, which is actually 1. 0 0 1, like that. You're actually removing one bit. So when we go from 1 0 1, we can go to the parent node by removing the leftmost. Similarly, 1 1 0, you can remove that and you get back there. So what is the purpose of this? Well, the idea is that the ranges of the summations are going to be the significance of an array at index x is that it is the summation from the parent all the way to itself. So let's just express this using sigma. It might be easier to express here. It is the summation from the parent of x up until x. And what this allows us to do is now we have a set of disjoint ranges. So let me reiterate. The idea is that we can calculate the parent at any time by removing the rightmost least significant bit. And that will be a constant time operation. Since we know what the parent is, we can dictate that the value of the summation from this element is all the numbers from the parent up until and not including that current element. or you can set it to include it. It doesn't really matter. But the idea is that since you have this range, you can just keep removing bits if you want to get a specific range, and you'll be able to get to whatever specific number you want to get to. So let's go through an example here. So if we have 1, 1, 0, goes to 1, 0, 0, and then it goes to 0, right? If we go from the 6. So if I want to range from 6 to 0, I'd hop from this 6 over here. I'd remove the rightmost and it sends me to the 4, and then the 4 would send me to the 0. And this would give me a range of roughly 0 to 6. So let's change this so that you start at 1 less here, and then it goes up to and including the x. So here we got a range from 0 to 6, and then we said that 6, the 6th node here in this array, contains elements from 4 to 6. Now the 4th one contains elements from 0 to 4, and then the 0 contains 0 to 0. By the way, the 0 node here will be a dummy node, just so you guys know in advance. This will be a dummy node. Okay, so now that I mentioned it a little bit, let's just go into some details about how we get the parent node. And after we get to the parent node, we're going to actually get to figure out how this algorithm works and doing some examples, because right now it's probably not very clear. So here's one other observation. For the algorithm to work, we need to realize that how do you remove the rightmost bit? So algorithm if we have a number x, we do bitwise AND x minus 1. This will actually remove the rightmost bit, because if we see here, we have any number and we subtract 1, what happens is it will carry here, and it'll borrow the carry until we get to the next most item. So if we do this, it actually removes it. So like I said, you can show a simple little proof, because all the bits to the right of the rightmost, like least significant set bit, they will all become 1 because you need to carry. So all of these zeros will become 1. And then when you have 0 and 1, ANDed, you get 0. And then once you get to this one over here, well, this one over here will become 0 because you need to borrow from it. And then you never traverse more to the left. So for that reason, 1 and 0 are also 0, therefore it works. Just a little bit of intuition. So we have this algorithm here. You'll commonly see this one. This one, I sort of came up with it when I was reading about binary Fenwick trees. There's another approach that people use, and instead the other algorithm that they use is saying that x minus equals x and negative x. So this is the secondary approach people use for removing the rightmost bit. The way this one works is that when you take the negative of a number, so let's go back to our example with the 1, 0, 0, 1, 0, 1, 0, 0, 0, 1. Oops, actually what am I doing? I don't need both. 1, 0, 0, 1, 0. When you take the negation, because we're using 2's complement, we're actually going to flip all the bits, and then we're going to add 1 to it. So this will be 0, 1, 1, 1, 0. Don't need that. And these. And this will actually give us, over here, as you can see, this one and this one, everything else is different. It gives us a 1 here, this. And then when you subtract that, because the other one was also set to 1, you're actually going to end up with 1, 0. 1, 0. Pencil doesn't work down here. which actually removes it for you. So the intuition behind that is that what you're doing is you're flipping all the bits. So by default, since you're flipping all the bits, when you AND it, it will return 0 because all of your bits are flipped. But then, afterwards, you add 1. So when you add 1, the rightmost bit, if it's 0, becomes 1. Okay. Now, when we have this number over here that ends in a 0, and then we have flip it becomes a 1, and then we add 1, so then it'll just keep carrying until it gets to a 0. Now, when it gets to the 0, wherever the original number had the rightmost bit set to 1, that will be a 0 in the case where you flipped all the bits, and then that will become 1. Hopefully this becomes clear. And then the moment you have 1 and a 1, the carry stops moving leftwards, and then you will maintain that 1. Hopefully this makes sense. Anyway, now that we have these two components down, we have the mechanism for actually doing the rightmost bit, and we also have two sample algorithms for computing that. So now let's figure out how to do the summation down the tree. So anytime you have one of these numbers, you're going to want to actually traverse up the tree, adding up all the summations. So you can get these powers like I mentioned before. So let's just erase these right now to make some more space. So what happens is, you end up getting some number. Let's take 5. So we have 1, 0, 1. Okay, so we have 5, and now we want to calculate the summation from 0 to 5. Alright, so basically what the algorithm does is it takes 101, gets the summation from that, then it goes up to its parent, which is 100, then it goes up to its parent, which is 0. So the summation function is actually very simple. You'll realize that the code in this implementation is not very sophisticated, because you don't actually need it to be sophisticated. Leveraging these bitwise algorithms, you can actually do it very simple, a couple lines of code. So we're going to write our method here into sum. So we want to go up to some number m. So we have our result here, which is 0. Now while m is greater than 0, because we said we'd have a dummy node, I'm going to say sum plus equals array m, and m minus equals m and negative m. So here, alternatively, you could have done m equals m and m minus 1, which would also work. Now just return the result. So what actually happens here is you're actually going up the tree because you already know your node and you want to add up all the intervals. So here you're actually constructing this component over here. So you're starting off at some x1, then you go to the x2, x3. So this is our x1 over here, x2, x3. Okay, so hopefully that makes sense here. Now for the update is relatively simple as well, but the update works in sort of the other direction, where you actually want to make sure you update all instances of that number throughout the entire binary index tree. So how does that part work? Well, we recapped this part where we said we're going up the tree. The second part that we need to mention is going and updating all the nodes. So if I were to update, let's say, update the number 3 in this tree that we have over here, I'm actually going to be influencing the 4 and the 2, because the 4, we said, goes from 0 to 4. And actually, wait, I don't influence the 2. Let's say I update 2. Then I change from 0 to 2, like this. Okay? So now that we have these two, like that, set, we need to update both of these nodes. Now, the way to update both those nodes, we need to clearly go through multiple renditions of it. One observation is that there's only going to be finitely many nodes that have overlapping. So in worst case, we'd say we'd have ON complexity. But there's also none of the children node of 2 need to be accounted for, because it'll be accounted for when we do the summation and it's going up the tree. So we really only care if there is another node that overlaps with its range. So if it overlaps with its range, it must be a number that is larger than it. So we know that all the bits to the right of that number, all the 0 bits leading up to the most significant rightmost bit, cannot be set. Now we also have all the bits to the left of that. There we have a bit of uncertainty. How do we know that it'll overlap and there won't be a parent bit, that will already take into account those nodes? So when we have a value like 0, oh, my pencil stopped working again. When we have a value such as 0, 1, 0, and we say we need to update it, how do we know that 0, 1, 1, for example, won't also be affected by it? It's because when we remove the rightmost significant bit, we get 0, 1, 0. How do we know that 1, 1, 0 doesn't need to be updated by that node? The thing is, the way it works is you actually need to add the same number of bits, but you need to add the rightmost significant number to it and essentially increment through all nodes that could possibly be child of it. And the way you perform that is you use the same algorithm that we used before for removing the rightmost bit, but instead we add the rightmost bit to it. If we observe in the 0, 1, 0 case, if we add the rightmost bit to it, we get 1, 0, 0. If we keep doing that until we run out of items in the array, it'll actually take into consideration all elements that we need to take into consideration of in order to get to where we need to get. So in order to do that, we're going to have the following method to implement for update. So we're going to have a void increment that looks as follows. So it's going to be void increment so P is how much we increment by. So here we instead go the other way. While m is less than n, array m plus equals p, m plus equals m and negative m, and that's it. So here we're clearly not returning anything, and we're also going to be iterating through all the elements, and we just keep adding the rightmost significant bit to it. So in the case of 0, 1, 0, we get to 1, 0, 0, and then we keep adding 1 to it to advance forward. By doing this, this allows us to essentially not go previously like the 0, 0, 1 case, and only consider items that would have a potential overlap. Now, talking about time complexity, which is a very important topic, let's show why it's log n. So for the query, I'd say it's fairly clear that it's log n because every time we're removing the rightmost bit, and there's only so many rightmost bits that you can have. At most, you would have 1, 1, 1, 1, 1 all the way, which is log n of the actual value because you're doing a base 2 binary representation of the integer. Now, on the contrary, when we have increment, we would instead have also have only log n because every single time we're adding the rightmost one, and it'll never overlap to affect the ones to the right of it. So if we add 1 every single time, even if we have like 1, 1, 1, 1, 1, 1, 1, it'll actually only happen log n times, again because we have base 2. So yeah, with all this said, this is the implementation, and then we have log n space because we're storing an array of size n plus 1, where 0 is the dummy node. So yeah, I hope you guys enjoyed this video, and if you have any questions, feel free to ask below. And yeah, thanks for watching.